Okay, so hi everyone. So in this video, I'll try to um, discuss about the problem, which is designing a key value store. Okay, so basically, let me just start off with all the references that I used to prepare my notes. So most of the information are from the system design book, the blue one, system design interview volume 1. And so and then also I have executive .io. That's a website for learning, reading and learning stuffs about anything. So from there also I have tried going through what kind of explanation they have for this same problem, and of course the internet. So that's what the all resources are there. And I'll just try to explain like whatever I could come up with the design using these resources, of course. So yeah, let me just start off. so so designing a key value store, right? So you can see it has it is also some sort of a storage system. Okay, so as we have database storage system, right? So in the similar manner, we have some we need to design some sort of a storage system, which is like but apart from the not irrespective of the relational database, we are just focusing on key value store. So why it is named as key value store is because we just need to have some sort of a storage system where we could store our data actually in a term in the form of key value. Okay, so it's not like relational database. Okay, so it's completely different from there. What do we have in relational database, right? So we have different tables in a database, and then we could kind of and this is also in a tabular format, and then we can have some sort of keys, and then we try to make a ER diagram and everything. But this is not the use case of that. Okay, so basically we just need to create a storage system, but this is a non-relational storage system. Okay, now we just have to cater these two functionalities, which are the top functionalities, there is put and get. Okay, so input, what do we have? You can see we have two parameters, which is like key and the value. This value is actually the user's data that user want to store. Okay, and basically these are kind of like public API that we'll have, and whenever user fires something with the key and the data, this will be stored somewhere in our key value store. Okay, and the get is like if you pass the key that you had used to store the data, it will give you the same data back. This is a very simple, you can say, functional requirements. Okay, so we have a get and we have a put. Okay, so input, it will store the value with assigned key. Okay, yeah, so one thing that you can see over here is basically that there are some techniques to kind of compress the data. Okay, so if you guys have heard about encoding techniques and all, right? So what happens, like, we want to have some sort of a space optimization here, right? Or like whatever you can say, just to store, because if let's say you had a 1 GB of data, okay, and you stored this raw data in the DB or in the key value store. Instead of what if I just have some mechanism to compress it without losing, without losing the originality of the data, okay, what if I just compress it and I store it somewhere else, and this is now in 0.5 GB. This is even better, right? So we have different sort of in techniques like encoding. So you can see one is like run length encoding, where we have, let's say, this whole thing is our data, and instead of that we kind of compress it, and then we just store A5. So we kind of decode this during the retrieval. We just decode it and give the original data. Okay, so that is one pretty quick like one point that you can mention. Okay. Cool. Now non-functional, of course we want our system to be scalable. Now these are pretty generic non-functional requirements. Okay. Scalable, like why do we need it scalable? Because let's say because we will not be having just a single server to handle the loads. So basically, let's say we have to store let's say some sort of petabytes of data, right? We need to store that petabyte of data. It's not just about storage, it's also about the retrieval process. Okay, so let's say there is an user who's firing the get key, okay, for its, and what happens is okay, this is mostly like a availability thing or low latency thing, but you can just assume there is this user. We need to make it to cater to a large number of users. Large numbers of users means large number of requests, and for that we can just not have one machine to handle all of this. Okay, so there will definitely be more than one servers for our key value store. Okay, now availability is definitely important. Okay, so basically let's say we had like 3 nodes serving users, and if one of the nodes gets down, still that system should be available. Okay, system should be consistent, because whatever data, right, whatever data that user has put in the DB, right, and if somebody tries to retrieve that data using the same key, he should get the most recent written data, right? It should not be like the data here was A and I'm getting B as an output for a particular key, right? So that is one thing that also need to be considered. Fault tolerant is same as in the events of failures, it should be available. Okay, and low latency, as I was speaking, like let's say there are users, you don't want to, and he fires a get key design, right, and he fires like the get API, he uses the get API, and you don't want user to wait for a longer period of time, so that's fine. Okay, cool. API design is also same. This is how our API design will look like. Okay, now just let me see like if there is something else. Yeah, so you can see like there is an arrow that I've made over here. So basically this is something to do with the cap theorem. Okay, and I'll not be discussing cap theorem, but you need to discuss the CA part of it, like what are the trade-offs that we can have, basically, right? Those are the things that we need to talk about in the interviews, or even just you need to have that in mind. Okay, Cool. Let's move on. Yeah. So as we discussed, right, uh, like how is our data is going to be stored, okay? And let's try to discuss first the scalability issue, okay? So let's say when we have like very big amount of data, okay, um, cool, right? So we all, you might have heard of different techniques to, or different techniques to handle or store these data, right? And data partitioning is one of those techniques, right? Now there are several data partitioning techniques as well, right? So we'll be discussing one of those data partitioning technique, which is consistent hashing. Like you can, if I go over here, that's how, that's what we'll be eventually using. But before that, you can just imagine, right? Let's say we have n servers, okay? We have n servers, right? And we have like k objects, okay? So I think I've already written it over here. So cool. Yeah. So we have n servers and k objects. Like this is the same problem. Like how are we going to distribute, some sort of like k kind is doing people evenly? That's what consistent hashing actually solves. But there are other constraints as well. We want to distribute it evenly. We have to look at even the replication factor here, right? We need to with the minimal movement of the data, because here the number of people, or you can say number of servers, since it's a distributed system, can go down, okay? So some servers can just get out of next moment we will not have n servers. Some servers might crash and get out of the system, right? Then okay, so that's the same data should be still there among n-1 servers. So the problem is not just to distribute, as well as to have some sort of rebalancing done or redistribution done as well, without lot of data movement. Okay, so that's the problem with which consistent hashing solves. Before that, if we just have to do that, okay, if we don't know about caching, consistent hashing or not, okay, we can just think of this sort of algorithm. We can just mod it, right? We can just mod this percentage n. Okay, so whatever let's say the object values, whatever it is coming, and then we can just mod it, and whatever number it comes, we can just assign it to the same server. Okay, so that's that's one way of dealing with it. But in this, you can imagine what happens if, let's say, one server goes down. Now you have to redistribute everything again. Okay, that's the thing that we don't prefer this one. Okay, of course this is also workable, but the redistributing of again the whole data among 3 servers now, like earlier we had 4, now we had just 3 servers. Now redistributing the same data among 3 servers will first require what? Will require data movement from 2 to 3, and we also have to think about the replicas of data on which other servers we are trying to keep. So basically, and it might happen like now the same hash value. Okay, so earlier this value was corresponding to 1, now it's corresponding to 2, right? So now this data need to be moved to 2. Like as in this case 2 is not there, but let's say if it was 3, right? So it has to be moved to 3 now. So that's why we don't prefer this. Okay. Now a better way is consistent hashing. Okay. After this, I might be showing you implementation of consistent hashing as well. So basically, consistent hashing solve this problem. So what do we do? You can imagine, people call it like as a ring or something, but you can just imagine it's some sort of a, because in granular level, right, in a low level implementation, right, will not have something sort of ring, like, right, we can, you can think some sort of a deck queue. You can, I think you can do it using deck as well. You can assume some sort of array vector, anything, okay, where we can just push this. Or basically how I had implemented it was using tree map. So tree map in Java, right, and it had a functionality called as tail map, right. So using this tail map, I could find the next node, for a key, and then I would go and I would assign this to the tail map. So let me just directly show you the implementation. Okay, so if something else comes up, then just forgive me if, because this is my iPad, so I hope this is where it is. Yeah, here it is. Okay, so I'll just show you the implementation. So you can just imagine what are the methods that we'll have for consistent hashing. We'll have add node, right? So we will have remove node and all, everything. So keeping those things in mind. Yeah, so I also had number of replicas. So this is the hash function. You can see this is the MD5 hash function, which is used in Amazon DB as well, right? So I think DynamoDB uses these hash functions as well. Okay, so this is message digest. We have add node function, and then we have remove node. We have get node count. That is fine. The most important function is this one. So I hope I could mark it. It's the get node function, right? So if you can see, we are trying to search a position for a key, okay, like which server does this key goes to. So we create a hash of we take the same hash of the key using the same hash function, okay, and then if this hash ring doesn't contain this hash, right, if it already contains, then we just get the hash of that, meaning that okay, now this hash will be actually the server, and we'll just put this key to that server. As you can see, this is a sorted map of integer and string, okay, where integer is the hash and string is, you can say, the server. Okay, if you see it in the main.java, this is how we have passed that we want to create a consistent hashing using these nodes. So something like that here also. So basically this is an important part that you can see. This is a get node function. So if the key is not present, then what we do, we create a tail, which is hashring.tail map, and we kind of if this hash, okay, if this tail which is coming, if that is empty, right, then we go to the first key, right. So if while starting from very first node and we go and we end up at the very first again, so we'll just store the first, to the first server only, okay. Otherwise this is some sort of, you can say, a lower bound on a number, okay. So if we go outside the array or outside the tree map, you come back and just put hashring.first key, okay, if that is empty. If not, then whatever comes just after that, just store it there, like basically you map it to that. So that's how it is. There is a concept of replicas as well. There is another problem with this. Even if you go and try to run that code in your local, you'll see like a lot of the keys, will be kind of hashed to a single server, which creates a problem, saying that like we have so many servers, but only one server is kind of catering a lot of, so that becomes a hot, what do you call, hot partition or something, hot point. Okay, so we don't want to have hot points in our hash ring. To tackle with this, basically you can see, if you just put more servers in your hash ring, basically then the ring will be kind of uniformly distributed, and then the probability that a key goes to a single server reduces, because we now have more servers. But there is a software way to do this as well, or you can say algorithmic way to handle this as well without adding physical servers. Okay, we can just hash the same value again, and we can create more virtual node corresponding to a single node. Okay, so this is kind of referring to this node. So this is S0 dash is kind of referring to this. If a key comes and falls over here, okay, if a key comes and fall over here, it is going to be stored in S0 only. Okay. Cool. Moving on. Yeah, so we have Amazon DB uses this, CDN also uses this. Consistent hashing is pretty useful. They use it in load balancers as well. Okay, people who don't know what load balance is, basically to distribute servers, requests to servers evenly. See, wherever we have these some sort of even distribution, data partitioning and all, we can use consistent hashing. Okay, let me just let's try to discuss this. Okay, or maybe we should go in a story manner. Okay, so cool. How much have we recorded? Already 22 minutes. Cool. So data replication I've already told. Like these green routes, we can just decide how many replicas do we need. Like, and now when a server goes off, we just move this data to the next two servers, and the data movement now becomes very less. That's another counter that we can say with respect to the previously that we were doing, just a raw hash function, right? Yeah, so let's talk about consistency. Okay. So now you can see, as we said, right, the data is replicated to multiple nodes, right? So there is some sort of synchronization that we'll need, right? Let me just try to make this down. Okay. Okay, that was okay. So let's say these are the three replicas, or you can say these are the three servers where we will be storing our node, storing our data. Okay. Cool. So what do we have actually is like we have a coordinator. So we have a coordinator which kind of Okay, this is basically kind of useful in order to decide which server it goes to. Like we can have some sort of coordinator in our code, just modifying that consistent hashing code that we did, right? So basically that's not in a real scenario, that's not how the code would be. Just a simple example. Yeah, so we have a coordinator, and we have decided that for a particular let's say a key, right, that our data will go to these three servers. Okay, and okay, so let me just write this. That's how it is, right? Now how do we confirm that this data has been written? There are a lot of things, right? A lot of ways that we can do, right? We can just receive an acknowledgement back, and as soon as we receive an acknowledgement, we say that okay, yeah, cool, the data is written, and then maybe we can inform our user as well. Cool. Now this is there are a lot of things that we can do with this to improve the consistency, or we can play with the whole CAP or CA thing, right? So according to the book, right, we have like n, we can define three things, which is n, w, and r, right? Okay, so n is the total number of servers. Okay, total number of servers where our particular data is being stored. You can say number of replicas. Okay, now w is what they call like quorum, right? Quorum of size w, but it's very important to understand what does that mean, right? So basically w is the definition of when do we say that a write operation is successful. Okay, so if we receive w acknowledgements, okay, then we say ki this is a write is successful. This is a read quorum. Okay, read quorum is again the same. When do we say that a read operation is successful? So basically read operation, so let's say if somebody fired a get query, okay, and when do we say that the read is successful? When our replicas basically gave the responses, and then we say like okay, the read is successful. Okay, now using these combination, right, we can have different values of r and w, okay, among n. Okay, total number of replicas is n only, right? So you can imagine that w will be less than equal to n, r will be also less than equal to n, right? We cannot have that many. Okay, so there are few numbers that we can say. You can imagine, like, let's say I say, man, like what did I do? I just make it n only. Now this becomes very highly consistent, right? Because I'm checking all the acknowledgement. When I'm reading, then also I'm checking all the replicas, right? But that is a very high number. Basically there is a combination on the basis of w plus r. If this value is kind of less than equal to n, okay, then they say that strong consistency is not guaranteed. If this is greater than equal to n, Okay, so if n was, let's say, 4, and this is something like 2 plus 3, okay, then that's good consistency, right? You can imagine like there are 2 write quorums and 3 read quorums, right? So we are kind of, there are a lot of checks happening basically before giving the data, right? And that's how we can imagine stuff, right? Okay, so on that only we have like different consistency model, strong consistency model, okay, and then we have weak, I think, and then we also have something like eventual. Eventual basically means over the time it will become consistent, okay. Just a fact, even DynamoDB and I think Cassandra, they both have adopted, or you can say they both work on this eventual consistency, because in that DB it's mostly like you are trying to make it faster, okay. It's okay if you for a period, I think, if you return a stale data, that's okay, I guess. So that's what the trade-off I was talking about, CA trade-offs, right? Here if you just make it very consistent, right, it will take time for receiving 3 acknowledgements, right, rather than just 1 acknowledgement. You get it, right? Cool. So this was a problem of having consistencies sorted out, right? So having okay, now let's move to the we can talk about basically concurrent issues, I guess, or you can say like inconsistency as per the book. Inconsistency of the data. How do we resolve that? Okay? Inconsistency resolution. Okay? So if we have inconsistent data, how do we resolve it, right? Right. So we should have some sort of mechanism for that, right? So you can just imagine that we have like server 1, and then we also have another server, and we are trying to write to a DB, or let's say there is some sort of get request, okay, or at the same time you can imagine that 2 users trying to put a key comma value, same key value, okay, right? So basically you can imagine for the same key we have like different values. Okay, how do we handle this? Yes, value 2, value 1. Okay, how do you handle this, right? Now if let's say a user reads from this DB, then he's getting value 2 for the same key, and if a user reads from this, right, if a user read from this, then he'll be having a different value altogether, right? Okay. Right, so you can just imagine that this can be a problem and we need to try to find a solution with this. Now if you see this is some sort of a inconsistency problem, and also you can say I'm not sure, but in concurrency problems, right? So you can say that if there is a concurrent update, how will you handle those? So this is a very very common scenario in terms of database and other things as well, in basically in overall software engineering, right? So how do we handle this, right? So there is something called as vector clock. Okay, so vector clock, we have a server and the version. Okay, so this is the server in which the data was written to, and we write it along with the version, right? And what happens is we keep on increasing this server. Let's say if the write was handled by server 1, next time we'll increase the server by +1. Okay. If the write was handled by some other server, then we have some sort of technique like this. Okay, this is how we can create a vector clock. So basically this is some sort of a versioning that we are introducing in our database, okay, to handle this inconsistencies problem. Okay, so what happens, let's say, let's try to think. Somebody first time the write was handled by a server 1. Okay, user 1 came, read, and it tries to write, and that was handled by server 1. And then we have, then the vector clock would be something like s1 comma v1. Okay, or we can just write like this as version 1. Next time also it was, let's say, written by this value, so we'll just increase the value. Okay, and we can have like d2, something like that. Now let's say network partitioning happened, or you can say write was handled by 2 different servers, which are s2 and s3. Now we'll have 2 different versions for the same data, right? So we'll have s2 comma 1, and if I have to, so I have to write s3 comma 1, s2 comma 1 is already there, right? I think I did somewhere. Okay, now that's what happens. Now there are 2 different versions of the same data. Okay, this is the same scenario over here. So user 1 request was handled by s2, and this was s3. So their version they are different versions. Now let's say another user comes in, he tries to read the data from here. Okay, then he reads the data from here. Okay, now he finds it different. So now he comes to the resolution part, and let's say this time the write was handled by some server 1 only, so that then the whole versioning becomes something like d of s1 3, and then s2 1, s3 1. That's why it becomes, it's very simple like that. So that's how you can use vector clocks to basically deal with the inconsistency issues. Okay, cool. So moving on now, there is another concept of how do you detect failure or some server going offline. So this is again pretty basic stuff. Let's say these 4 servers are where are kind of communicating in between. So one very common way is that we can just have everybody ask everybody, this ask each one of them. Okay, this asks all of them, okay, are you alive, are you alive, are you alive, right? But this is, and if that is kind of pretty time consuming task. Okay, so what we can do, and there's a better way to do this, so we call it gossip protocol. Okay, so basically what each server will have a map, and they will send a heartbeat from time to time. Okay, so they will have a map of, this is called a membership list, whatever it is, it doesn't matter what name we give, right? So, and timestamp, so we'll have a timestamp and the heartbeat count. If the heartbeat count is still stationary for a long period of time, it assumes that this is kind of, this server is failed, so we need to handle this. So this is the what we're discussing here, failure detection, right? So we can edit it. Okay, cool. So I think you can just, this is the failure detection in the server. Okay, there are another failure detection, like how do you handle the request when a data is some sort of lost, or whenever we say data is lost, basically our data center goes down, or fails. So how do we handle those things, right? So I think for now, I think I'm good with these requirements and these main things. Now maybe in a later part of the video we will have some sort of, before wrapping up, we can draw a high-level diagram for this. I think that should be good. So basically we'll have our client, okay, and client will do get put from here, and this is our hash ring, and we have all the nodes happening. Okay, so this is the Mac. You can edit like this, and what else can we have? So let's say we have a group handling. So we have a group of this. This is a part of the group. Okay. So basically they will be communicating with each other. Cool, like this. Okay. And basically each node can have different things. Okay, cool. Now if you're wondering where these actually, how the data will be stored, because you can see, like, we never talked about where the data will be stored, but it will be stored in server itself. Each server will have a disk, right? And we can store that. We can even use the cache of that server to to make some retrievers faster, right? So let's have a client again. So we'll kind of go to a very right. So let's try to analyze one server. Okay, so this is a server. Okay, now you can see this server is like your laptop or computer, right? You can imagine like that. And this will have a disk, right? You can make a disk over here, and then we can also have a cache of the server, right? So basically what we can have, whenever write operations happen, right? So whenever something like write is happening, then we can just imagine it is going to cache, and then it is kind of flushed, and we can have, so there is something called SS tables. This is where we'll be actually storing our key value. Okay, right? We can also have some sort of commit log. Okay, this sort of logs, you can see it in append log only thing, some sort of strategies that databases have, okay, to retrieve the data, after an offset. Okay, okay, the read will happen from cache. So during the read part, it will happen from cache. If it's not present there, then the cache will go and ask the disk from the disk to fetch the data. Okay. So that's how whole system will look like. There are a lot of things like to consider here and to talk about. Cool. Okay, then I'll wrap up now.